Greetings and welcome to a lesson on quadratic equations with complex solutions. I'm your presenter, Lynn Mann. In this lesson, we have 5 primary objectives. We're going to define what complex numbers are. We're going to do some arithmetic with complex numbers. We're going to add, subtract, multiply, and divide. We're also going to solve quadratic equations that have complex solutions. I'd like you to take a little bit of a journey with me through your past up to your near future. And your history working with numbers mimics the history that humans have been working with numbers. And here's what I mean. In your infancy, when you were little, you really kind of only needed counting numbers. 1, 2, 3, 4, 5. In fact, those are the first numbers you ever learned. And in fact, in the human history, those were the first numbers as well. We needed to keep track of objects, and therefore we invented counting numbers, also called natural numbers. They happen in the natural world. 1, 2, 3, 4, and so on. Those were the first numbers you learned. Those were the first numbers that humans invented. Yes. Invented. I said invented. We didn't discover them, we invented them. And it came a point in time in your life and in human history that the natural numbers, it just wasn't enough. We needed more. Here's what I mean. I have 2 pins in my hand. If you come and take those 2 pins, how many pins do I have left? Now, you, as brilliant as you are screaming, 0, 0. But wait a minute. Think about your history. You don't have the number 0. So what do as a clever human being? You say, wait a minute. I need something to represent this having nothing. So we invent 0. Now 0 is an amazing number. It not only represents having nothing, it also is a placeholder in our Arabic style of writing numbers, and it is a transitional number, and you'll see that in just a sec. So it meets 3 really important criteria that we needed as human beings for our number system. So we have the natural numbers. The natural numbers with 0 are the whole numbers. But again, once upon a time in your life, you needed more than that. And same thing with humans. Now I'm going to give you a very simple math problem that you will probably know the answer to immediately. So 2 minus 3. What's the answer? Aha! No solution. And you're like, what? Remember, these are the only numbers we have. There is no solution to that problem. Well, we needed a solution to that problem. So what did humans do? We developed more numbers to represent going back and back and back. And it was primarily for the financial that we've gotten to a point in human history where we needed to show debt. And so negative numbers were really an ideal way of showing debt. Things that you owed me. You owe me money, right? So out of necessity, humans needed negative numbers, and now you can solve a problem like 2 minus 3. It's -1. It exists now. And as we travel through your history, we're also traveling through human history, and again, a point in time in your life that this wasn't enough. Because what if you only take half of something away from me? You break it, and you take one side and I take one side. And I said something really important. I said half. But we don't have a number to represent that right now, do we? No. You have 1 part out of 2 and I have 1 part out of 2. Aha! Well, let's develop another set of numbers that includes these integers because I can write integers in this special format. And this special format is a whole number over a whole number. And you might be screaming at me, hey, wait a minute, you have 2.3. Yes, but I can write that as a whole number. I can say that is 2, I can say that's 23 over 10. And therefore, it is a rational number. Rational numbers are very precious to us. We work with them all the time. So do you. You may not like working with rational numbers, aka fractions, but they're needed. Now, rational numbers can be written as decimals if they end, like 2.3 stops, it terminates. 1 over 9, or 1/9, can be written as 1.11111, where the 1 never stops. It repeats. So rational numbers are decimals that end up being able to be terminated or repeating. Well, what happens to those numbers that don't repeat and don't terminate? Do we not have them? Absolutely, we do not have them right now. But as humans, we have need of those numbers, like the square root of 2. And therefore, what did we do? We invented them, of course. So we have irrational numbers like pi, the square root of 5, 7 square roots of 8. So we now have the rational numbers and irrational numbers. And most of your math career lately has been in these two areas, which are the real numbers. You put natural numbers inside whole numbers, inside integers, inside rationals, and irrationals. You put them together and you are in the real numbers. Now, up to this point, for your history of math, this is really pretty much all you've needed. But in the history of humans, we had problems very similar to that 2 minus 3 business where we stamped on a no solution. We had these problems that had no solutions. And those problems included any issue with a square root of a negative number does not live in the real number group. It's not there. It doesn't exist. But we've had these problems where we work through the problems and all of a sudden, inside the problem, before we get to a solution, we get the square root of a negative number. Now, proof-wise, the general sense, there were mathematicians that proved there is a solution. But algebraically, we couldn't find a solution. And so those two things just didn't match up until someone realized, well, you know what? Why don't we just break up that square root of that negative number into the square root of -1 times the square root of that positive number, because we're totally allowed to do that with square roots. And they said, well, we'll just, have that square root of -1 float around. And once they did that, they had a huge breakthrough and solved the math problem. Now, even the guy that invented that said it was just a, trick, a math trick, and really didn't take it all that seriously until math progressed and we really, really needed it. So you may have seen the square root of -1 be written as I. So we now have the real numbers and we have imaginary numbers. Now, they're horrible names for these sets of numbers. We really shouldn't call them imaginary because imaginary makes it feel like they don't exist, and they absolutely exist. They exist as well as natural numbers exist, as well as integers exist. They exist. And we shouldn't call them imaginary numbers, but we do. So any value that has a square root of a negative number, that is an imaginary number. When we put real numbers and imaginary numbers, you have now reached your near future. Complex numbers. You've reached your near future, and in fact, you have actually reached where the rest of humans are. We have no numbers past this. These are the only sets of numbers that currently exist. Kind of cool that you've reached our limit of our sets of numbers. But is that the end? I don't know. At the time we only had natural numbers, we thought that was the end. And when we had integers, we thought that was the end. That's all we needed until we needed more. So who knows? Maybe in my future, maybe in your future, maybe there's another set past these complex numbers that we will need in the future. But we're not there yet. We're only on the complex numbers, and so are you. So now let's talk about I. The definition of I is the square root of -1. And if you square I, that is the square root of -1 times the square root of -1, which is -1. I is the imaginary unit. As we saw in our picture regarding complex numbers, they are real numbers and imaginary numbers. But complex numbers specifically have two components. So if z is our complex number, it is composed of a real part, a, and imaginary part with an I. Now a and b are real numbers, right? So that could be 2 plus 3i. But I represents negative square root of 1, so that bi component is the imaginary part, the a is the real part. Complex numbers in the standard form is a plus bi. It could also look like a minus bi if b is negative. If a is 0 and b is not 0, in the standard form, it would be written as 0 plus bi. But we can write it simply as bi, which is purely an imaginary number. Likewise, if b is 0 and a is a real number, we call that a real number. But we can also write it as a complex number as a plus 0i. Okay, here's where you are allowed to have more power with math. You are now allowed to take the square root of a negative number. For any positive number b, the square root of negative b is going to be the square root of b times I. Let me give you an example. So I can write the square root of -3. This technically breaks down into the square root of -1 times the square root of 3. Square root of -1 is I, so I get I times the square root of 3. Okay, now I want to identify just the real part and the imaginary parts of each of these complex numbers. Now, let's take them one at a time. For a, 2 plus 5i, the real part is 2 and the imaginary part is 5. Okay? I is the stand-in for, hey, I'm imaginary, so the imaginary part is 5. For b, think about this. What's the real part? What's the imaginary part? The real part is 7. The imaginary part is -1/2. What about c? What's the real part? What's the imaginary part? Now you might be saying, hey, there's no real part, but remember we can rewrite this as 0 plus 3i. So the real part is 0 and the imaginary part is 3. What about 9, -9? Think about how you can rewrite it in the standard form of a complex number. This would be -9 plus 0i. So the real part is -9, the imaginary part is 0. What about 0? Think about how you can write that as a complex number. 0 plus 0i? Absolutely. Real part is 0, imaginary part is 0. What about 3 plus the square root of -25? That's the square root of a negative number. How can we write that square root of a negative number? Well, that's the square root of -1 times the square root of 25. Square root of 25 is 5. The square root of -1 is I. So we can rewrite that as 3 plus 5i. So the real part is 3 and the imaginary part is 5. Now with real numbers, or at least rational numbers, we had what we said is equivalent fractions. So 1/3 equals 2/6. Those two things are equal to one another. In complex numbers, for two complex numbers to be equal to one another, the real components must equal the real component, and the imaginary components must equal each other. So the real parts equal each other, and the imaginary parts equal each other. So now we don't know the whole entire problem here in terms of what the value of x is and what the value is of y is. But we can certainly put this together. Let's let our first number be z, our complex number z, and that's 3x minus 1 plus 5i. Let's let a second complex number, let's say w, equals 8 plus 3 minus 2yi. Then, here's what we have. Remember, the real parts must equal each other, and the imaginary parts must equal each other. So we have 3x minus 1 equals 8. 3x minus 1 is the real part. 8 is the real part. So those must equal each other. The imaginary part, 5, and the imaginary part, 3 minus 2y, those must equal each other for these two values to be equal to one another. So now I have two small algebraic problems that I need to solve. 3x equals 8 plus 1. X must equal 3. And likewise, for the y, 5 minus 3 equals negative 2y. 5 minus 3 is 2. Divide by negative 2 and we get y equals negative 1. Just like with real numbers, you learned how to add, subtract, multiply, and divide real numbers. And yes, some sets of real numbers had different rules about them than other. For example, adding and subtracting negative numbers have different rules than just adding positive numbers. Fractions have different rules than whole numbers. So yes, we have different rules here as well. So let's take two complex numbers z and w. Z is a plus bi. W is c plus di. And keeping in mind, a, b, c, and d are just real numbers. They could be fractions, they could be negative numbers, they're just real numbers. So let's look at adding these two numbers up, z plus w. That would be a plus bi equals c plus di. What we're going to do is we're going to take the real parts and add them together. We're going to take the imaginary parts, add them together, and then we're going to make sure that we label the imaginary part with our I. So we would get a plus c plus b plus d I. Subtraction works similarly. If we're going to subtract two complex numbers, z minus w, we're going to take z, a plus bi, and subtract c plus di. Again, we have the real components, the imaginary components, and the label for the imaginary value. And therefore, a minus c plus b minus d I. Add the real components, add the imaginary components. It's very similar to adding and subtracting like terms. If you treat that I like a variable x, the rules are pretty much the same. Let's work through a couple of examples on adding and subtracting complex numbers. Let's take A. 3 plus 7i is our first complex number plus 2 minus 4i. I'm going to combine the real components and the imaginary components. So I have 3 plus 2 and 7i plus a negative 4i. I get 5 plus 3i. You can also think of it as just adding like terms. I added the constants together and I added the variable i's together. If you want to think of adding and subtracting like that, it's perfect. Let's try b. I have 5 plus 9i minus 6 minus 8i. And according to the rule, I subtract the real parts and I subtract the imaginary parts, keeping in mind that is a negative 8i. And two negatives make a positive, so I've got 5 minus 6 is negative 1 plus 17i. You can also think of it as distributing this negative just like you would if that variable wasn't an I, but it was an X. That's what you would do. It's the same thing. It will come out to be the same thing. C, 2 minus negative 2, real parts. And I want to rewrite this negative 9 square roots eventually, but let me just write it down as square root of negative 9 minus the square root of negative 4. Now the square root of negative 9 will be 3i. Square root of negative 1 is I, square root of 9 is 3. Minus square root of negative 4, well, that's definitely an I, and then what's the square root of 4? 2, so that is 2i. And negative in the negative is a positive. And now it becomes adding like terms. 4 plus 3 minus 2 is 1i, or 4 plus I. Just like with any 1 in front of a variable, we don't have to write it. We can imply that there is a 1 there. When we multiply complex numbers, one way of doing it is to remember this formula. A plus bi times c plus di will equal a times c minus b times d plus a times d plus b times c, I. Certainly you could memorize that if you wanted. Or let's see how this comes about by using some techniques we already know. If this I was just an X, what would you do? Well, wouldn't you FOIL? So let's go ahead and FOIL this. A times C is AC. A times DI is ADI. BI times C is BCI, and BI times DI is BDI squared, because I times I is I squared. Now I have some like terms here. Okay, so AC plus AD plus BCI. I squared is the square root of negative 1 squared, which is negative 1. So therefore, this is BD times negative 1. All right, we have AC plus AD plus BC times I. Negative 1 times BD is minus BD. And now, this is a real number. This is a real number. I'm going to combine them. AC minus BD plus AD plus BC times I. And that's what that is. So you can either remember this formula, or we can just use a skill we already know, which is let's FOIL it. The only thing we have to remember is if we get an I squared, we have to change that into a -1. Let's do a couple of examples of multiplication with complex numbers. 3 minus 5i times 2 plus 7i. Now, I don't have that other formula memorized, and I don't mind foiling values like this, binomials like this, so I'm going to go ahead and use what I know about foiling, but then I want to make sure if I run across any I squares that I change those over to -1s and maybe have to do a little bit more math. 3 times 2 is 6. 3 times 7i is plus 21i. I'm treating I like it's just a variable. It could be x, it could be y, it could be z. -5i times 2 is -10i. -5i times 7i, well, -5 times 7 is -35. And I times I is I squared. Aha! I've got to turn this I squared into a -1. So that is -35 times -1. So here's my problem so far. 6 plus 21i minus 10i plus 35. Negative times negative is positive. Now I combine like terms. 6 plus 35 is 41. 21 minus 10 is 11i. So 41 plus 11i. Let's try B. Now B, yeah, I could put a 0 in front here, but that's kind of overkill. So I'm going to go ahead and leave it as is and just distribute this -2i to both terms in the parentheses. -2i times 5 is -10i. -2i times -9i is positive 18i squared. But again, that's not just a plain old variable anymore. I'm going to have to take care of this I squared, and it is -1. So a positive 18 times a -1 is a -18. But this is not in standard form. The imaginary part does not come first in standard form. The real part comes first. So -18 minus 10i would be our answer. I want to talk about just, a warning to you about dealing with square roots. So if we have the square root of a times the square root of b, that will equal the square root of ab. All of those values are positive. A is positive, b is positive, and since you multiply a positive times a positive is a positive. But it doesn't work when you have negative values in there. The square root of -9 times the square root of -9 is really 3i times 3i. 3i times 3i is 9i squared. I squared is -1, so it is a -9. If we would have done this directly, we would have said -9 times the square root of -9. Well, that's the square root of -9 times -9. But that's the square root of 81, which is 9. No, those two things are not the same. We need to convert them over to the imaginary value first before carrying out the multiplication. Let's try a few examples involving these negative roots. We'll take them one at a time. So let's look at the square root of -2 times the square root of -8. We do not want to just combine them now. We need to change them over to imaginary numbers first. The square root of -2 is 2i. The square root of negative 8 is 8i. This 2i times 8i is 16i squared. But remember, I squared is really negative 1, so this is negative 16. Okay, let's try B. I'm going to convert all of the square root of negative values over to i's first. This is 3i times 2 plus 3i. Now I can do my multiplication without breaking any of the rules, without causing any more complexity. Okay, 3i times 2 is 6i, and 3i times 3i is 9i squared. But don't forget, you have to convert this I squared to a negative 1. 9 times negative 1 is really negative 9, but this is not in standard form. We need to switch the order. Here's the imaginary part, here's the real part. The real part always comes first. Negative 9 plus 6i. All right, let's try another one. Negative 2 plus the square root of 3 squared. Okay, doesn't look like any issues yet, right? There's no negative in that square root, so let's go ahead and take it as is. Negative 2 plus the square root of 3 times negative 2 plus the square root of 3. Now I'm just going to treat this like normal. Negative 2 times negative 2 is 4. Negative 2 times the square root of 3 is negative 2 square roots of 3. 3 times negative 2 is negative 2 square roots of 3. And square root of 3 times the square root of 3 is square root of 3 squared, which is 3. Let's add like terms. 4 plus 3 is 7. A negative 2 square roots of 3 and a negative 2 square roots of 3 is negative 4 square roots of 3. No i's involved here. We're kind of growing our skill set. Okay. All right, here we go. Now we have those square roots of negative numbers. We have imaginary parts. First things first, I'm going to rewrite these in terms of I, not the square root of a negative number. 3 plus 2i. 1 plus 32i. From here, I'm going to FOIL. 3 times 1 is 3. 3 times positive 32i is 96i. 2i times 1 is plus 2i. 2i times 32i, well, 2 times 32 is 64. I times I is I squared. Now, I've got to take care of that I squared. This is negative 1. Okay, here's my problem. 3 plus 96i plus 2i minus 64. I'm going to add the real parts together. I'm going to add the imaginary parts together. 3 minus 64 is negative 61. And 96 plus 2 is 98i. Okay, so let me just recap really quick. When we added or subtracted complex numbers, we would kind of do, well, we would do the real stuff together and we'd do the imaginary stuff together. When we multiplied complex numbers, we really used the same technique that we've used in the past. We've either distributed the number into the parenthesis or we FOILed. The only thing we had to watch out for is if we ended up with I squared. We had to change that to convert it over to -1. Now we talked about adding, subtracting, multiplying, and division. We're working up to division. For division, we need to have a value that kind of gets rid of imaginary parts of numbers. And that is going to be the conjugate of the complex number. The conjugate of a complex number is changing the sign in front of the imaginary part only. Here's what I mean. Let me give you a few examples of some imaginary numbers here. So this big long line over our complex number means conjugate. If I have a value 3 plus 2i, 3 plus 2i, the conjugate of that will be 3 minus 2i. Let's go with 5 minus 1/4 I. Okay, well, if we want the conjugate of 5 minus 1/4 I, we're going to change the sign that's in front of the I value. So 5 plus 1/4 I. Now, what if we have a -2 plus 4i? What would be the conjugate? Okay, -2 plus 4i. Its conjugate is going to be -2 minus 4i. Remember, when we take the conjugate of a complex number, the only sign we are changing is the one directly in front of the imaginary component. So let's just finish this off. If I have a -1/3 minus 10i, the conjugate will be -1/3 plus 10i. We need the conjugate to be able to do division of complex numbers. Well, let's try it out. Let's take a complex number and multiply it by its conjugate and see what we get. First of all, I have a is our complex number, z equals 2 plus 5i. I need to figure out what z conjugate is, so z with the bar on top of it. Our conjugate will be 2 minus 5i. All I do is change the sign in front of the imaginary component. Now I want to know what z times z bar is. Z is 2 plus 5i, and z bar is 2 minus 5i, or z conjugate, I should call it. I'm going to go ahead and FOIL this guy. 2 times 2 is 4. 2 times -5i is -10i. 5i times 2 is plus 10i. And 5i times -5i is -25i squared. I have that I squared I have to deal with. This is really -1. So a -25 times a -1 is a positive 25. 4 minus 10i plus 10i plus 25. Now I'm going to combine what I can. Well, 4 plus 25 is 29, and a minus 10i but a plus 10i goes away. Oh, well, that's interesting. I don't have any imaginary component. It's just a real number. Okay, 29. All right, let's try another one. Z equals 1 minus 3i. Let's multiply it by its conjugate. I got to figure out its conjugate first. So conjugate of z is 1 plus 3i. Now let's multiply the two of them together. Z times z conjugate is going to be 1 minus 3i times 1 plus 3i. I'm going to go ahead and FOIL this. 1 times 1 is 1. 1 times 3i is plus 3i. Negative 3i and a 1 times 1 is negative 3i. And negative 3i times positive 3i is negative 9i squared. All right, I got that I squared again. So that's really negative 1. And a negative 9 times a negative 1 is a positive 1. 1 plus 3i minus 3i plus 9. Combine like terms. 1 plus 9 is 10. 3i minus 3i goes away. And I'm left with only the real number 10. And in fact, any time that you multiply a complex number by its conjugate, you will only be left with a real number. And in fact, there's a whole theorem about that. So if we have a value, z equals a plus bi, then z times its conjugate will always be a squared plus b squared. Kind of cool. We can jump to the answer by doing a squared plus b squared. So I'm going to go ahead and grab the 2 plus 5i. So let's try this out. Z equals 2 plus 5i. The conjugate of z is 2 minus 5i. And if this works, we should get 29. Right? We got 29 doing it the long way. We should get 29 here. A is 2, and therefore 2 squared is 4. B is 5, and therefore b squared is 25. And 4 plus 25 is 29, and yes, yay, we have a shortcut we can use. Nice. Really, really nice. Now, why do we need the conjugate? We're going to use the conjugate to divide complex numbers. In other words, if we have a complex number in the numerator and a complex number in the denominator, we are going to multiply both the numerator and the denominator by the conjugate of the denominator, and that will be our division. That's our process for division. Another way of looking at this is we do not want complex numbers in the denominator. And to do that, to get rid of a complex number in the denominator, we know we can multiply it by its conjugate. But we can't just multiply the bottom number by the conjugate and do nothing to the top. So we do both. Now that we know how to multiply by its conjugate, and we kind of have a shortcut where z times z conjugate is a squared plus b squared. Now what we're going to do is use this technique to divide complex numbers. As long as we are not dividing by 0, because that's still not permitted, this will work. If we have a complex number w and we are dividing it by another complex number z, we are going to multiply both the numerator and the denominator, because this is in essence a fraction, by the conjugate of z, and that will be our result for dividing by complex numbers. Ultimately, we get rid of the complex number in the denominator and it becomes a real number. So let me show you how this works. Okay, if I am dividing by a complex number, I am, in essence, going to multiply both the numerator and the denominator by the conjugate. Okay, my conjugate of the denominator is 2 minus I. 2 minus I. Now, I have the shortcut to deal with that denominator. I am forcing that denominator to be a real number, and I have that a squared plus b squared trick. A is 2, so that's 4. And the number in front of the I is 1, and 1 squared is 1. So I know my denominator is 5. 4 plus 1 is 5. Now I need to do the numerator. 1 times 2 minus I, well, 1 times anything is that thing. So the numerator, and I don't necessarily need the parenthesis anymore, so I won't write it. 2 minus I. That is already in standard form, so I'm going to go ahead and put a box around it and call it that is my solution. Let's try another division problem. 4 plus the square root of negative 25 all over 2 minus the square root of negative 9. Now I'm not going to work with the negative square root or the square root of a negative number. I'm going to change those over to imaginary numbers. 4 plus 5i and 2 minus 3i. Okay, well now I can do this division right here. This is 4 plus 5i divided by 2 minus 3i. To do that division, I'm going to multiply it by the denominator's conjugate. 2 plus 3i. 2 plus 3i. Both to the numerator and the denominator. I can't just do one, I have to do both. I got to keep things balanced. I do have the nice trick, or shortcut, I should say, not trick, shortcut to get the value in the denominator. Let's take a and square it, that's 4. Let's take b and square it, so negative 3 times negative 3 is 9. And so I can simplify the denominator to be 13. Great. I do have to do the math in the numerator. I'm going to FOIL it. So 4 times 2 is 8. And I probably didn't give myself enough room, but I'll manage. 4 times 3i is 12i. And in fact, I really didn't, so I'm going to get rid of that for now. 5i times 2 is positive 10i. And 5i times 3i is positive 15i squared. Remember, I squared is negative 1. So here's what I have. 8 plus 12i plus 10i minus 15 all over 4 plus 9. I'm going to simplify this as much as I can. 8 minus 15 is negative 7. 12i plus 10i is plus 22i. 4 plus 9 is 13. My answer to 4 plus the square root of negative 25 divided by 2 minus the square root of negative 9 is negative 7 plus 22i all divided by 13. You may not have used complex numbers in the real world up to this time, but complex numbers do have a place. Remember, the reason why we create more and more numbers, that we invent more and more numbers, is because we have needed to invent more numbers to find solutions to problems. And one area where complex numbers does work really well to have is in electronics and electrical engineering. So here we have an example of using complex numbers in AC circuits, alternative current circuits. So in a parallel circuit, the total impedance, Z, is given by this formula. Z of t, so the total, equals Z1 times Z2 divided by Z1 plus Z2. Now we want to find Z, the total, assuming that we know Z1 equals 2 plus 3i ohms, measurement, and Z2 equals 3 minus 4i ohms. Iohms? I ohms. All right, so here's what I need to do. I'm going to first figure out z1 times z2. And then I'm also going to figure out z1 plus z2. And then I'll put these two together to actually do that division. So z1 is 2 plus 3i. z2 is 3 minus 4i. And I'm just going to use my FOIL method. It works really well. So why do something that ain't broke, right? 2 times 3 is 6. 2 times negative 4i is negative 8i. 3i times 3 is positive 9i. And 3i times negative 4i is negative 12i squared. Aha! I squared. Anytime I see it, I really try to change it now so I don't forget later. Negative 12 times negative 1 is positive 12. So I have 6 minus 8i plus 9i plus 12. Combine like terms. Combine the real parts, combine the imaginary parts. 6 plus 12 is 18. Negative 8i but plus 9i is a positive 1i, or just I. Okay, cool. I've got that z1 times z2 component. Now let's figure out z1 plus z2, and then we'll put it all together and do the division. z1, 2 plus 3i, plus z2, 3 minus 4i. Add the real parts, add the imaginary parts. 2 plus 3 plus 3i minus 4i. I just rewrote it so I have the real parts together and the imaginary parts together. 2 plus 3 is 5, plus, well, that is a negative I, so I'm going to go ahead and say minus I. All right, so we know z1 times z2 is 18 plus I, and we know z1 plus z2 is 5 minus I. This is now the division we're going to do. To do division of complex numbers, I do need to multiply by the conjugate. It would have been very, very messy to try and do it when it was all kinds of z's and lots of components. So by reducing it first to a singular complex number divided by a singular complex number, it does make it a little bit easier. So let's now multiply by the conjugate. 5 plus I, 5 plus I. All right, I'm going to go ahead and bring this off to the side so I have a little bit more room to FOIL. 18 times 5, is that 90? That looks like 90 to me. 18 times I is plus 18i. I times 5 is 5i. And I times I is I squared. And I'm going to go ahead and do our shortcut for the denominator. If you want to FOIL it, you can. 5 times 5 is 25, plus 1 times 1 is 1. Now I just need to make sure I change over my I squared to a minus 1. I have 90 plus 18i plus 5i minus 1 all over 25 plus 1. The only thing I did was convert that I squared to a negative 1. Combining like terms, I get 90 minus 1 is 89. 18 plus 5 is 23i. And 25 plus 1 is 26. Now it's great and wonderful to be able to do some arithmetic on a new set of numbers, the complex numbers. Adding, subtracting, multiplying, dividing. Check, 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 check. We have built up our math skills throughout your years. Each time we throw in some more numbers, we teach you those four things: adding, subtracting, multiplying, dividing. We did it with whole numbers. We did it with fractions. We did it with decimals. We did it with square roots. We taught you at each stage, each time we added more numbers to your knowledge base of the set of numbers that you're aware of, we taught you those four things: adding, subtracting, multiplying, dividing. We've done that to ultimately be able to solve problems. We're to the point we are now solving quadratic equations with complex solutions. What I want you to keep in mind is you know how to solve these things. You do. You know how to solve these things by factoring, by quadratic formula, by completing the square. You have learned a lot of ways to solve quadratic equations. Now you just have to keep in mind, what about I? I is going to be floating around in the problem somewhere. Sometimes not at all until the end, and sometimes, yeah, in the beginning, and we have to carry it through. So here we have two equations, and you've probably seen these before. Here's what we did before. Our A is x squared plus 4 equals 0. And once upon a time ago, you said, oh, well, I'm just going to bring this 4 to the other side, and I get x squared equals minus 4. And then you learned a technique. Oh, when I have an x squared, I can take this square root and the square root, as long as I do the plus and minus on the right-hand side, and I get x equals plus and minus the square root of negative 4. And once upon a time ago, you used to say, no solution, right? You said there is no solution. Ah, but that's when you were in the real numbers, and you were only allowed to play with the real numbers. Now, you're also allowed to play with complex numbers. So there is a solution now. The square root of negative 4 is 2i. So we have x equals plus and minus 2i. Your solution is a complex, well, it's an imaginary number. If I threw a 0 in front, then it would be complex. It's purely imaginary. Let's go ahead and try another one. Another problem. B. X squared plus 2x plus 2 equals 0. All right. Well, let me see. Can I factor it? No, it really doesn't look like it's factorable. Do I want to bother completing the square? Well, I could. Move that 2 over, complete the square. Yeah, let's try that. All right, so x squared plus 2x plus something equals the negative 2, because I brought that over to the other side, plus something. What is that something? Okay, well, I got to take this 2, and I divide it by 2, and I square it. So 1 squared is 1. So that's what I'm going to add to both sides. Okay, now I'm going to factor the left-hand side, and I get x plus 1 squared, and negative 2 plus 1 is negative 1. Okay, and now I'm kind of back in the situation where I was in part A, where I've got something squared equals something. So I'll just take the square root of both things. Okay, and I get x plus 1 equals plus and minus the square root of negative 1. Oh, and before, remember, we had no solution, but now we do. The square root of negative 1 is I. This is x plus 1 equals plus and minus I. I'm going to subtract 1 from both sides. I'm going to subtract 1 from both sides, and I get x equals negative 1, because these I can't combine. 1 is real, the negative 1 is a real number. The plus and minus I is imaginary. So if you want to break it apart, x equals negative 1 plus I, and x equals negative 1 minus I. I have two solutions. Likewise, over here, x equals 2I, and x equals negative 2I. Now, in that second example, I chose to complete the square, but I certainly could have used the quadratic formula and I would have gotten the same results, the same solutions. But there's something very special about the quadratic formula, which will tell us what types of answers, types of solutions we will have. This part of the quadratic formula, not even the square root part, just the b squared minus 4ac part. This is called the discriminant. And the discriminant tells us a lot of information. If we do that math, this value, b squared minus 4ac, could be a positive number. It could be greater than 0. Right? That's an option. It could be exactly 0. b squared minus 4ac could be less than 0. So b squared minus 4ac could be a positive number, if I could spell right. b squared minus 4a could be 0, or it could be negative. Those are our three options. If it is positive, we get two unequal real solutions. If it is 0, we get one real solution to the whole entire problem. And if it is negative, we get two non-real complex solutions. And in fact, the powerful part of this is they are conjugates of one another. They are conjugates. Let's use what we know about the discriminant to figure out how many solutions and what type of solutions we will have for each of these quadratic equations. For a, x squared minus 4x plus 2 equals 0, we know our discriminant is going to be, well, let's figure it out. Our discriminant is b squared minus 4ac. Our a value is 1, our b value is negative 4, and our c value is 2. So let's plug those in. Negative 4 squared minus 4 times 1 times 2. Negative 4 squared was 16. Negative 4 times 1 times 2 is negative 8. And so our discriminant equals 8. Now that's not the solution to the quadratic equation. This value of 8 just tells us that there are two real solutions, meaning the values, the solutions to this quadratic equation live in the real number world. There are two of them, b squared minus 4ac, where a is 2, b is 2, and c is 19. 2 squared minus 4 times 2 times 19. 2 squared is 4. 4 times 2 is 8. 8 times 19 is my calculator, 152. And 4 minus 152 is negative 148. Now again, the solution to the actual quadratic equation is not 148. But what this negative 148 tells me is that there are two complex solutions. Now, knowing what types and how many you have can really help you out in terms of if you want to stay in the real world, in the real numbers, and you find your discriminant is two complex solutions, well, again, our conjugates, you know you can stop there because there are no real solutions. Likewise, if you want to stay in the complex world and you find your discriminant gives you only 2 real solutions, then you know you're not in the right place. That's why it gives us some helpful information about what our solutions will be, and to not continue with a hard problem, right? If I'm looking for 2 real solutions and I find my discriminant says I have 2 complex solutions, I can stop because there are no real solutions. All right, last one. C. B squared minus 4ac, where a is 4, b is 4, and c is 1. 4 squared minus 4 times 4 times 1. Okay, 4 squared is 16. 4 times 4 times 1 is 16, and we get 0. This means we have 1 real solution. Could you imagine working with an incredibly difficult problem and you're looking for a second solution that doesn't exist? This tells us a lot of information. Once I find the one solution, that's it. There are no other solutions. I can stop working on this really hard problem. Okay, that is it for this lecture. We talked about what complex numbers are, how to add, multiply, subtract, and divide, and we also found complex solutions in quadratic equations. So we did quite a bit in this lecture. Until next time, be seeing you.